You're standing on a beach, holding a single grain of sand between your fingers. That tiny speck has witnessed more drama, more violence, more incredible transformations than any Hollywood blockbuster could ever imagine. It's been part of towering mountains, deep ocean floors, scorching deserts, and frozen glaciers. That grain of sand is older than every civilization, older than complex life itself, and it carries within its crystalline structure the memory of our planet's most extraordinary story. But here's what's absolutely mind-blowing. That grain of sand started its journey on a world so alien, so hostile, so completely different from today's Earth that you wouldn't recognize it as the same planet. We're talking about a hellscape that makes Mars look like a tropical vacation. No oxygen to breathe, no blue skies, no green plants, no solid ground to stand on. Just a molten ball of rock and metal spinning through space, getting pummeled by asteroids the size of cities. And somehow, through a series of events so unlikely, so perfectly orchestrated by the laws of physics and chemistry, that grain of sand became part of the most remarkable planet in the known universe, a world teeming with life, covered in vast oceans, wrapped in a protective atmosphere, and home to creatures so complex they can contemplate their own existence. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. By any chance, if your curiosity stretches beyond space and science, I would love to invite you all to visit and take a look at our new channel, Boring Money. A place where finance slows down and fortune gently drifts in. I have dropped a link in the video description. Do consider checking it out. Let's start. This is the story of how that transformation happened. How a lifeless chunk of rock became the vibrant living world we call home. It's a story that spans 4.5 billion years, involves cosmic collisions that would make your worst nightmares seem peaceful, and includes plot twists that would leave the best screenwriters speechless. I'm going to take you on a journey through deep time, where 1 million years passes like a single heartbeat, where continents dance across the surface like leaves in the wind, and where life itself becomes the ultimate architect of planetary change. We'll witness the birth of oceans, the rise of atmosphere, the emergence of the first sparks of life, and the countless catastrophes and miracles that shaped every mountain, every valley, every breath of air you've ever taken. But before we dive into this epic tale, let me share something that completely changed how I think about our planet's history. Last year, I was hiking through the Grand Canyon, staring at those magnificent layered walls of rock. My guide pointed to a single layer, maybe 6 inches thick, and said something that gave me chills. That layer represented more time than all of human civilization. Every empire that ever rose and fell, every war ever fought, every love story ever lived, all of it compressed into a band of rock thinner than this book. That's when it hit me. We're not just living on Earth. We're living on top of the most incredible story ever told, written in stone, hidden in ice, preserved in fossils, and encoded in the very atoms that make up our bodies. Every element in your body, except hydrogen, was forged inside a dying star and scattered across the cosmos before eventually finding its way to this small rocky planet orbiting an ordinary yellow star. The story I'm about to tell you isn't just about rocks and minerals and ancient climates. It's about you. Because understanding how Earth evolved helps us understand how we evolved. Every breath you take connects you to the earliest organisms that learn to harvest energy from sunlight. Every heartbeat pumps blood that contains iron, forged in stellar cores billions of years ago. Every thought you think happens because of an atmosphere that took billions of years to develop the perfect chemical composition for complex life. And here's what makes this story even more incredible. Scientists have only recently figured out how to read the clues that Earth has been leaving for us all along. We can now decode the messages hidden in ancient rocks, extract climate data from ice cores thousands of years old, and trace the chemical signatures of life itself back to its very beginning. We're living in the golden age of understanding our planet's past, and the discoveries being made right now are rewriting textbooks faster than they can be printed. So buckle up, because we're about to embark on the ultimate time travel adventure. We'll start at the very beginning, when Earth was nothing more than cosmic dust swirling around a young star. We'll watch as gravity performs its patient magic, pulling matter together grain by grain, collision by collision, until something resembling a planet begins to take shape. But this isn't the Earth you know. This is a world of unimaginable violence and chaos. Picture a planet where the surface temperature exceeds 2000 degrees Fahrenheit, where massive impacts happen so frequently that the entire surface stays molten like a global ocean of liquid rock, where the atmosphere is made of vaporized rock and metal, and where a day lasts only about 6 hours because the planet spins so fast that it's practically flinging itself apart. This is the Hadean Eon, named after Hades, the ancient Greek underworld, and for good reason. If you could somehow travel back 4.5 billion years and observe Earth from a safe distance, you'd witness a hellscape beyond imagination. Asteroids and comets slam into the surface with such frequency and violence that the entire planet glows like a coal in a furnace. The impacts are so intense that they literally blast pieces of the planet back into space, where they orbit like a ring of molten debris before eventually falling back down as a rain of fire. But here's where the story gets interesting. Even in this apparent chaos, the fundamental forces of nature are already at work, laying the groundwork for everything that will follow. Each impact, each collision, each moment of apparent destruction is actually part of a construction project that will take hundreds of millions of years to complete. The first major milestone in Earth's evolution happens when our planet gets big enough to hold onto an atmosphere. Not the atmosphere we breathe today, but something far more primitive and hostile. This early atmosphere is made mostly of hydrogen and helium, the same gases that dominate the giant planets like Jupiter and Saturn. But Earth is too small and too close to the Sun to hang on to these light gases for long. The solar wind, a stream of charged particles flowing outward from our star, gradually strips away this first atmosphere, leaving our planet temporarily naked in space. But nature abhors a vacuum, and Earth quickly develops a second atmosphere, this time built from gases released by volcanic activity and asteroid impacts. This new atmosphere is dominated by water vapor, carbon dioxide, nitrogen, and other gases that pour out of the planet's interior through countless volcanic eruptions. The surface is still too hot for liquid water to exist, so all that water vapor just hangs in the atmosphere, creating a thick, choking blanket of steam that traps heat and makes the surface even hotter. This is where one of the most important events in Earth's history takes place, though it happens so gradually that if you were watching, you might not even notice it at first. The Sun, which was about 30% dimmer than it is today, begins to settle into a more stable pattern of energy output. Volcanic activity on Earth's surface starts to decrease as the planet begins to cool down. And slowly, over millions of years, the temperature drops to a critical threshold. For the first time in Earth's history, water begins to condense. Not just a little bit of water, but massive amounts of it, falling from the sky in what might have been the longest, most intense rainstorm in the history of the solar system. Picture rain falling continuously for thousands, maybe millions of years, filling every crater, every valley, every depression on the planet's surface with liquid water. This is the birth of Earth's oceans, and it's one of the most crucial moments in our planet's story. Because once you have liquid water, you have a powerful agent of change. Water dissolves rocks, carries sediments, creates chemical reactions, and provides the perfect medium for the complex chemistry that will eventually give rise to life itself. But we're still hundreds of millions of years away from that miraculous development. The early oceans are nothing like the blue waters we know today. They're hot, acidic, and loaded with dissolved metals and minerals. The water is probably green or orange or some other alien color, and it's constantly being stirred up by massive tides created by a moon that orbits much closer to Earth than it does today. These early oceans are more like a global chemical laboratory where countless experiments in molecular complexity are taking place simultaneously. Meanwhile, the solid Earth beneath these primitive oceans is undergoing its own dramatic transformation. The planet's interior is still largely molten, kept hot by the decay of radioactive elements and the leftover heat from all those early impacts. This molten interior creates the first version of plate tectonics, though it's much more violent and chaotic than the relatively stable system we have today. Imagine the Earth's surface as a thin skin forming on top of a pot of boiling soup. As soon as a solid crust begins to form, it gets broken up and recycled by the churning motion underneath. Volcanic activity is everywhere, creating the first primitive landmasses and pumping even more gases into the atmosphere. The chemical composition of both the oceans and the atmosphere is constantly changing as rocks dissolve, gases escape from the interior, and new minerals crystallize from the cooling magma. But perhaps the most important change happening during this early period is the gradual formation of the first stable continental crust. Unlike the dense, dark rocks that make up the ocean floor, this continental crust is made of lighter, more complex minerals that float on top of the denser material below like icebergs on water. These first continents are small and unstable, constantly being torn apart and reassembled by the violent geological processes operating on the early Earth. Yet even these primitive landmasses play a crucial role in Earth's evolution. They provide platforms where different types of chemical reactions can take place, sheltered bays where sediments can accumulate, and elevated areas where new types of weathering and erosion can begin to operate. Most importantly, they create environments where the chemistry of the oceans and atmosphere can begin to stabilize into something approaching the conditions necessary for life. As we move forward through this incredible story, we're about to witness one of the most remarkable transitions in Earth's history. The violent, chaotic world of the Hadean Eon is slowly giving way to something more stable, more complex, and infinitely more interesting. The stage is being set for the emergence of the first chemical systems that blur the line between non-living and living matter. The transformation we're watching isn't just about rocks and water and atmosphere. It's about the emergence of complexity from simplicity, order from chaos, and ultimately, consciousness from matter. Every step in this process builds on what came before, creating new possibilities, new environments, and new opportunities for even more complex developments. And we're just getting started. As the Hadean Eon draws to a close, something extraordinary begins to happen. The relentless bombardment of asteroids and comets that had turned Earth into a molten nightmare finally starts to ease. But this isn't just a gradual decline in cosmic violence. This is the end of what scientists call the late heavy bombardment, a period so intense that it literally reshaped the entire inner solar system. Picture the solar system as it was 4 billion years ago. It's like a cosmic shooting gallery where planets are getting pummeled by debris left over from the formation of the solar system itself. Mars gets scarred with massive impact craters that are still visible today. The moon's surface gets blasted into the heavily cratered landscape we can see with the naked eye. And Earth, being the largest target in the inner solar system, takes the worst beating of all. But here's what makes this story absolutely fascinating. Every one of those catastrophic impacts is actually delivering something precious to our planet. These aren't just random chunks of rock. These are cosmic delivery vehicles carrying water, organic molecules, and rare elements that Earth couldn't produce on its own. Comets from the outer solar system bring vast quantities of frozen water. Asteroids deliver carbon, sulfur, and complex organic compounds that formed in the cold depths of space. Think about that for a moment. The very water you drink, the carbon in your body, the elements that make life possible, all of it arrived during this period of apparent destruction. It's like the universe was simultaneously trying to destroy Earth and equip it with everything it would need to become a living world. The violence was creating the conditions for peace. The chaos was laying the foundation for order. As the bombardment finally begins to subside, Earth enters what geologists call the Archean Eon. This is when our planet truly begins to resemble something we might recognize, though it's still so alien that stepping onto its surface would be instantly fatal. The atmosphere is toxic, containing virtually no oxygen, but loaded with methane, ammonia, and hydrogen sulfide. The sky probably glows with an eerie orange or red color, and the landscape is dominated by countless active volcanoes belching out gases and lava. But beneath this hostile surface, something remarkable is happening in the oceans. The water has finally cooled enough for complex chemistry to take hold, and the seas become a vast laboratory where molecules are combining and recombining in increasingly sophisticated ways. The early oceans are rich in dissolved minerals, creating what some scientists call a primordial soup, though it's more like a concentrated chemical broth than anything you'd want to eat. This is where we encounter one of the most profound mysteries in all of science. Somewhere in these ancient seas, non-living matter crosses an invisible threshold and becomes something that can grow, reproduce, and evolve. The origin of life is still one of the biggest unsolved puzzles in biology, but we know it happened sometime during the Archean Eon, probably around 3.5 to 4 billion years ago. What makes this transition so mind-boggling is that it represents a fundamental shift in how matter behaves. Up until this point, everything on Earth followed the basic laws of physics and chemistry. Rocks formed according to temperature and pressure. Water flowed downhill because of gravity. Chemical reactions proceeded based on the properties of atoms and molecules. But life introduces something completely new into the equation. It creates systems that can maintain themselves against the natural tendency toward disorder. It develops mechanisms for storing and transmitting information across generations. It begins to actively modify its environment in ways that increase its chances of survival and reproduction. The first living things were probably incredibly simple by today's standards, more like self-replicating chemical systems than anything we would recognize as life. They might have been little more than strands of RNA or DNA wrapped in primitive cell membranes, floating in warm tidal pools or around underwater volcanic vents. But even these simple systems possess the fundamental characteristics that define life, the ability to reproduce themselves and pass on their chemical instructions to the next generation. And once this process gets started, it unleashes forces that will completely transform the planet. Because living things don't just adapt to their environment, they actively change it. They consume resources, produce waste products, and create chemical reactions that would never happen in the purely geological world. The first major transformation begins almost immediately. These early life forms start producing oxygen as a waste product of their metabolism. Now, this might sound like a good thing, since we obviously depend on oxygen to survive. But for the early Earth, oxygen was actually a deadly poison. The atmosphere and oceans were designed for a world without oxygen, and when this reactive gas starts building up, it triggers one of the most severe environmental crises in Earth's history. Scientists call this the Great Oxidation Event, and it represents the first time that life itself became a major geological force. Over the course of several 100 million years, oxygen levels in the atmosphere rise from essentially zero to significant concentrations. This oxygen reacts with iron dissolved in the oceans, causing it to precipitate out as rust-colored minerals that settle to the ocean floor in distinctive layers that geologists can still identify today. But the real drama happens when oxygen levels get high enough to become toxic to the very organisms that produced it. Most of the early life forms on Earth were anaerobic, meaning they couldn't tolerate oxygen. When oxygen concentrations reach critical levels, it triggers a mass extinction that wipes out huge numbers of these primitive organisms. It's like life poisoned itself with its own waste products. Yet this apparent catastrophe sets the stage for the next great leap in evolution. The organisms that survive the oxygen crisis are the ones that learn to use this reactive gas to their advantage. They develop new metabolic pathways that can harness the chemical energy stored in oxygen, creating much more efficient ways of powering their cellular processes. This is the birth of aerobic respiration, the process that allows complex life forms like us to exist. Oxygen-breathing organisms can extract far more energy from their food than their anaerobic predecessors, giving them a huge advantage in the evolutionary arms race. They grow larger, move faster, and develop more sophisticated internal structures. But perhaps more importantly, the rise of oxygen creates the conditions necessary for the next phase of Earth's evolution. Oxygen in the upper atmosphere gets converted into ozone, creating a protective shield that blocks harmful ultraviolet radiation from the sun. This ozone layer makes it possible for life to eventually move out of the protective depths of the oceans and colonize the land surface. Meanwhile, the solid Earth beneath the oceans is undergoing its own dramatic evolution. The early continents that formed during the Hadean Eon are growing larger and more stable. Plate tectonics is becoming more organized, creating the first recognizable patterns of seafloor spreading and continental drift. These growing land masses begin to have a profound impact on global climate and ocean circulation. They alter wind patterns, create barriers that redirect ocean currents, and provide elevated platforms where different types of weathering and erosion can take place. The chemical composition of seawater begins to stabilize as the violent volcanic activity of the early Earth gradually subsides. Perhaps most importantly, these early continents create shallow coastal environments where life can experiment with new forms and strategies. Tidal zones, lagoons, and inland seas become laboratories for evolutionary innovation. The interaction between land and sea creates chemical gradients and energy sources that don't exist in the open ocean. As we move deeper into the Archean Eon, life begins to organize itself into more complex communities. Instead of individual cells floating independently in the water, organisms start forming colonies, mats, and other cooperative structures. They begin to specialize, with different types of cells performing different functions within the same community. This is where we see the first evidence of what would eventually become one of the most important innovations in the history of life: the evolution of eukaryotic cells. Unlike the simple prokaryotic cells that dominated the early Earth, eukaryotes have complex internal structures, including a nucleus that contains their genetic material and specialized organelles that perform different cellular functions. The evolution of eukaryotic cells represents a quantum leap in biological complexity. These cells can grow much larger than their prokaryotic predecessors, store more genetic information, and carry out more sophisticated metabolic processes. They become the building blocks for all complex life on Earth, from the tiniest algae to the largest animals. But we're still talking about single-celled organisms floating in ancient seas. The evolution of multicellular life with specialized tissues and organs is still hundreds of millions of years in the future. Yet even at this early stage, life is already beginning to reshape the planet in fundamental ways. The story we're witnessing isn't just about biological evolution. It's about the co-evolution of life and Earth itself, a complex dance between living and non-living systems that will continue for the next 4 billion years. Every change in the atmosphere affects the evolution of life. Every evolutionary innovation changes the chemistry of the oceans and atmosphere. This intricate feedback loop between biology and geology is what makes Earth unique among all the planets we've discovered. It's not just that our planet happened to develop the right conditions for life. It's that life itself became one of the major forces shaping planetary evolution. And we're about to witness the next act in this incredible drama, as the stage is set for transformations that will make everything we've seen so far look like a gentle warm-up for the main event. As we venture deeper into the Archean Eon, Earth begins to reveal one of its most extraordinary secrets. Hidden beneath those ancient seas, something unprecedented is happening. Life isn't just surviving anymore. It's becoming an engineer, actively redesigning the planet's architecture from the inside out. Imagine diving into one of these primordial oceans 3 billion years ago. The water is still warm, tinted with minerals that give it an alien hue. But as you descend toward the sea floor, you'd encounter something that would take your breath away. Vast underwater cities built not of stone or metal, but of living organisms themselves. These are the first stromatolites, towering structures created by colonies of cyanobacteria that have learned to work together in ways that seem almost impossible for single-celled organisms. Layer by layer, generation by generation, these microscopic architects build massive limestone towers that rise from the ocean floor like ancient skyscrapers. Some of these biological monuments reach heights of several meters, creating the first three-dimensional ecosystems in Earth's history. But here's what makes these structures absolutely mind-blowing. They're not just random piles of bacteria, they're sophisticated engineering projects that create their own weather systems, their own chemical environments, and their own ecological neighborhoods. The bacteria at different levels of these towers specialize in different functions. Some harvest sunlight near the surface. Others process chemicals in the darker depths. Still others create the binding agents that hold the entire structure together. This is the dawn of ecosystem engineering, and it represents a fundamental shift in how life interacts with the planet. Instead of simply adapting to existing environments, organisms are now creating entirely new habitats that didn't exist before. They're not just passengers on Spaceship Earth anymore. They've become members of the crew. The impact of this biological revolution extends far beyond the ocean floor. Those cyanobacteria pumping out oxygen aren't just changing the chemistry of seawater. They're performing planetary surgery on the atmosphere itself. Every bubble of oxygen that rises from these underwater gardens is contributing to one of the most dramatic atmospheric transformations in Earth's history. But nature has a way of throwing curveballs just when things start to get comfortable. As oxygen levels continue to rise, Earth encounters its first major climate crisis. The methane that had been helping to keep the planet warm gets oxidized out of the atmosphere. Without this greenhouse gas, global temperatures plummet dramatically. Welcome to the Huronian glaciation, Earth's first ice age, and it's unlike anything our planet has experienced before or since. This isn't just a period of cooler weather. This is a deep freeze that lasts for nearly 300 million years, turning our planet into what scientists call Snowball Earth. Picture a world where glaciers extend from the poles all the way to the equator, where the oceans freeze solid to depths of several kilometers, where the only liquid water exists in deep ocean basins beneath miles of ice, or around underwater volcanic vents that provide just enough heat to maintain small pockets of liquid habitat. This frozen wasteland seems like the end of Earth's story, a cosmic dead end where life retreats to a few isolated refugees and waits for the planet to thaw. But here's where the story takes one of its most remarkable turns. Life doesn't just survive this global catastrophe. It uses the crisis as an opportunity to innovate in ways that will fundamentally reshape the future of evolution. Trapped beneath the ice, organisms are forced to develop new survival strategies. They become more efficient at extracting energy from limited resources. They develop new forms of cooperation and symbiosis. Most importantly, they begin experimenting with new cellular architectures that will eventually lead to one of the most significant innovations in the history of life. This is where we witness the birth of the eukaryotic cell, though the process is so gradual and so complex that it plays out over hundreds of millions of years. Some bacteria begin living inside other bacteria, creating the first endosymbiotic relationships. What starts as one organism eating another evolves into a partnership where both benefit from the arrangement. The bacteria that get consumed don't get digested. Instead, they set up shop inside their hosts and become specialized organelles. Some become mitochondria, the powerhouses that will eventually allow complex cells to generate enormous amounts of energy. Others become chloroplasts, the solar panels that will enable plants to harness sunlight directly. This cellular revolution is happening in slow motion by human standards, but it's creating the foundation for everything that will follow. These new eukaryotic cells are like biological Swiss Army knives, packed with specialized tools that allow them to exploit environmental niches that were previously inaccessible to life. But the real drama is happening on the planetary stage. As the Huronian glaciation finally begins to end, Earth doesn't just return to its previous state. It emerges from the deep freeze as a fundamentally different world, with new atmospheric chemistry, new ocean circulation patterns, and new opportunities for biological innovation. The ice sheets retreat, revealing continents that have been reshaped by hundreds of millions of years of glacial activity. Massive ice sheets have carved new valleys, deposited enormous quantities of sediment, and created fresh mineral deposits that will influence the chemistry of future oceans. More importantly, the end of the glaciation coincides with major changes in the solid Earth itself. The continents are growing larger and more stable. Plate tectonics is becoming more organized and predictable. The first supercontinents are beginning to form as smaller landmasses collide and merge into massive unified blocks. These geological changes have profound implications for life. Larger continents create more diverse environments, from mountain ranges to inland seas to vast river systems. They also influence global climate patterns, creating the first recognizable weather systems with seasonal variations, and regional climates. As we move into what geologists call the Paleoproterozoic era, Earth is becoming a world of unprecedented complexity. The atmosphere now contains significant amounts of oxygen, though still far less than today's levels. The oceans teem with diverse microbial communities that have learned to exploit every available energy source. And the solid Earth provides a stable platform for increasingly sophisticated geological processes. But perhaps the most remarkable development is the emergence of the first complex ecosystems. Life is no longer just about individual organisms struggling to survive. It's about communities of organisms that have learned to work together, compete with each other, and create emergent properties that are greater than the sum of their parts. In shallow coastal waters, vast microbial mats carpet the seafloor like living carpets. These communities include dozens of different species, each playing a specific role in the ecosystem's metabolism. Some capture sunlight and convert it to chemical energy. Others break down organic matter and recycle nutrients. Still others produce the chemical signals that coordinate the community's activities. These early ecosystems are creating their own local environments, complete with chemical gradients, energy flows, and information networks that rival the complexity of modern ecological systems. They're proving that cooperation can be just as powerful an evolutionary force as competition. The success of these microbial communities sets the stage for the next great leap in evolutionary complexity. Over the next billion years, some of these cooperative cellular partnerships will take cooperation to an entirely new level. Instead of just living together, they'll actually merge into single organisms with multiple specialized parts. This is the dawn of multicellularity, though we're still hundreds of millions of years away from seeing the first animals and plants. The journey from single cells to complex multicellular organisms will require innovations in cell-to-cell communication, tissue formation, and developmental programming that make our current understanding of biology look primitive by comparison. But even at this early stage, we can see the writing on the wall. Life has learned to engineer its environment, survive global catastrophes, and create new forms of complexity that seem to emerge from nowhere. Every crisis becomes an opportunity. Every limitation becomes a challenge to overcome. The Earth that emerges from the Paleoproterozoic era is a world poised on the brink of an evolutionary explosion that will make everything we've witnessed so far look like a gentle prelude. The stage is set. The players are in position. And the most dramatic acts of this planetary theatre are still to come. The chemical ingredients for complexity are now in place. The physical environments needed for experimentation exist in abundance. And life itself has become sophisticated enough to start writing its own evolutionary script. We're about to witness transformations that will create not just new species, but entirely new categories of existence. The age of visible life, of organisms large enough to see with the naked eye, is approaching, and with it will come changes that make our planet not just habitable, but spectacular in ways that no other world we've discovered can match. The story is accelerating now, building toward revelations that will reshape our understanding of what's possible when chemistry meets creativity on a planetary scale. As we cross the threshold into what scientists call the Mesoproterozoic era, Earth enters what might be the most mysterious chapter of its entire story. This is the period that paleontologists have dubbed the boring billion, though that name couldn't be more misleading. Because while the surface might look relatively peaceful, beneath the waves and within the microscopic realm, life is conducting some of the most audacious experiments in the history of evolution. Picture yourself floating above this ancient world about 1.5 billion years ago. The continents have grown into massive supercontinents that dwarf anything we see today. These colossal landmasses stretch from pole to pole, creating vast interior regions that experience climate extremes unlike anything in the modern world. Scorching deserts cover areas the size of entire modern countries, while massive inland seas create their own weather systems. But here's what would immediately strike you about this world. It's eerily quiet. There are no birds singing, no insects buzzing, no leaves rustling in the wind. The land is almost completely barren, painted in shades of red and orange from iron-rich rocks that have been oxidizing for hundreds of millions of years. Occasionally, you might spot a thin green film along the edges of rivers and lakes where the first pioneering microbes are beginning to test the possibilities of terrestrial life. The real action is happening in the oceans, and it's unlike anything Earth has seen before. The seas have become vast laboratories where evolution is conducting experiments that seem to defy the laws of physics. Single cells that have been cooperating for hundreds of millions of years are now taking cooperation to an entirely new level. Imagine watching this process unfold in extreme slow motion. Individual cells that had learned to work together in colonies are now experimenting with something revolutionary. Instead of remaining separate organisms that happen to live together, some of these cells are beginning to specialize so completely that they can no longer survive independently. This is the birth of true multicellularity, and it's one of the most profound innovations in the history of life. We're witnessing the emergence of organisms that are no longer just collections of identical cells, but integrated biological machines where different parts perform different functions for the benefit of the whole. The process is incredibly complex and happens in stages that span millions of years. First, cells within a colony begin to differentiate, taking on specialized roles like reproduction, feeding, or structure. Then, these specialized cells become so dependent on each other that they can't survive alone. Finally, the entire colony becomes a single organism with a unified identity and purpose. But here's what makes this transformation absolutely mind-blowing. These early multicellular organisms aren't just bigger versions of single cells. They're creating entirely new categories of existence. They develop internal communication systems that allow different parts of the organism to coordinate their activities. They create internal transportation networks that move nutrients and waste products throughout their bodies. They even develop primitive sensory systems that allow them to respond to their environment as unified entities. Some of these early multicellular pioneers remain microscopic, but others begin to grow to sizes that would be visible to the naked eye if anyone were around to see them. We're talking about organisms that might be several centimeters across, true giants by the standards of their time. The implications of this multicellular revolution extend far beyond biology. These new organisms begin to interact with their environment in ways that single cells never could. They can build more sophisticated structures, exploit new energy sources, and create more complex ecological relationships. In the deep ocean, some of these multicellular pioneers begin constructing what can only be described as biological cities. These aren't the simple microbial mats of earlier eras, but complex three-dimensional structures with multiple levels, specialized neighborhoods, and sophisticated waste management systems. They create their own local climates, their own chemical environments, and their own ecological rules. Meanwhile, the planet's geology is undergoing equally dramatic changes. The supercontinent that had dominated the earlier part of this era begins to break apart, creating new ocean basins and new opportunities for biological innovation. As these continental fragments drift apart, they create narrow seaways where ocean currents can flow in new patterns, mixing nutrients and creating new marine environments. The breakup of the supercontinent also triggers massive volcanic episodes that pump new chemicals into the atmosphere and oceans. These volcanic events aren't just random geological accidents. They're part of a complex feedback system between the solid Earth and the biosphere that will continue to shape planetary evolution for billions of years to come. But perhaps the most significant change during this period involves the evolution of sexual reproduction. Up until this point, most organisms reproduced by simply making copies of themselves. But some of these new multicellular organisms develop the ability to combine genetic material from two different individuals, creating offspring that are genetically unique. This innovation might seem minor, but it's actually one of the most revolutionary developments in Earth's history. Sexual reproduction allows organisms to shuffle their genetic information in countless new combinations, dramatically accelerating the pace of evolutionary change. Instead of waiting for random mutations to create new traits, organisms can now generate genetic diversity through the simple act of reproduction. The effects of this genetic revolution ripple through every aspect of life on Earth. Organisms become more adaptable, more resilient, and more capable of responding to environmental changes. They begin to evolve at unprecedented rates, creating new forms and strategies that would have been impossible under the old system of asexual reproduction. As we move deeper into this era, the pace of change begins to accelerate noticeably. New types of cells appear with increasing frequency. New forms of metabolism evolve to exploit previously untapped energy sources. New ecological relationships develop between organisms that had previously lived in isolation. But the most remarkable development is the emergence of what scientists call eukaryotic complexity. These aren't just larger cells or more sophisticated colonies. These are organisms with internal architectures that rival the complexity of modern cities. They have specialized compartments for different cellular functions, internal transportation systems, sophisticated quality control mechanisms, and even primitive forms of memory that allow them to learn from experience. Some of these complex eukaryotes begin to experiment with predation, actively hunting and consuming other organisms instead of just filtering nutrients from the water. This creates the first true food webs, where energy flows from one organism to another in complex chains of consumption and recycling. The emergence of predation triggers an evolutionary arms race that will continue for the rest of Earth's history. Prey organisms develop new defenses like protective shells, toxic chemicals, and rapid escape mechanisms. Predators respond by evolving more sophisticated hunting strategies, better sensory systems, and more efficient digestive processes. This predator-prey dynamic creates selective pressures that drive organisms to become larger, faster, more complex, and more intelligent. It's like evolution has suddenly shifted into high gear, creating innovations at a pace that makes the previous billion years look almost static by comparison. As we approach the end of the Neoproterozoic era, Earth is poised on the brink of one of the most dramatic transformations in its entire history. The groundwork has been laid for an explosion of complexity that will make everything we've witnessed so far look like a gentle warm-up exercise. The oceans now teem with microscopic ecosystems of unprecedented sophistication. The chemistry of seawater has stabilized into something approaching modern conditions. The atmosphere contains enough oxygen to support more energy-intensive forms of metabolism. And most importantly, life has developed the genetic and cellular tools necessary for the next great leap in evolutionary complexity. We're standing at the threshold of what paleontologists call the Neoproterozoic era, a period that will witness the emergence of the first truly large, complex organisms. These won't be microscopic creatures visible only under powerful magnifiers. These will be organisms you could hold in your hand, examine with the naked eye, and recognize as fundamentally different from anything that came before. The stage is set for the appearance of the first animals, the first plants, and the first ecosystems complex enough to be called forests and reefs. We're about to witness the transformation of Earth from a planet dominated by invisible microbes to a world where life becomes a spectacular, visible presence that reshapes every aspect of the planetary environment. But before we get there, Earth has one more surprise in store. The planet is about to experience another series of global ice ages that will make the earlier Snowball Earth episodes look like mild winter weather. These coming glaciations will test life's resilience in ways that push evolution to its absolute limits, creating the conditions necessary for the most remarkable biological innovations in Earth's history. The story is building toward a crescendo that will change everything. We're approaching the moment when Earth stops being just another rocky planet with some interesting chemistry and becomes something unprecedented in the known universe. A world where complexity, beauty, and intelligence emerge from the patient work of physics, chemistry, and time. The transformation that's about to unfold makes everything we've witnessed so far look like a gentle rehearsal for the main performance. As Earth enters the Neoproterozoic era, roughly 1 billion years ago, our planet becomes the stage for evolutionary experiments so radical, so unprecedented, that they will redefine what it means to be alive. But first, nature decides to throw one final curveball that will test life's ingenuity in ways that seem almost impossibly cruel. The planet is about to enter another series of global ice ages, but these aren't just cold snaps. These are freeze events so severe that they make the earlier Snowball Earth look like a mild winter day. Picture this: glaciers advancing from both poles simultaneously, meeting at the equator to create a world encased in ice from top to bottom. But this time, the ice doesn't just cover the land. It extends out over the oceans, creating a frozen shell that's several kilometers thick in some places. The entire planet becomes a giant snowball, spinning through space, reflecting almost all of the sun's energy back into the void. Under this global ice sheet, life retreats to the most extreme refuges imaginable. Deep ocean vents become isolated oases where communities of organisms huddle around volcanic heat sources like survivors around a campfire. Pockets of liquid water trapped beneath miles of ice become evolutionary laboratories where innovation happens under the most intense selective pressure Earth has ever created. And here's where the story takes a turn that's so dramatic, so unlikely, that if you read it in a science fiction novel, you'd probably think the author was getting carried away. Instead of simply waiting out the freeze, life uses this crisis as an opportunity to make the most audacious leap in complexity that evolution has ever attempted. Trapped in these isolated refuges, organisms begin experimenting with body plans that seem to violate everything we know about how simple creatures should behave. They start building internal skeletons, developing sophisticated digestive systems, and creating sensory organs that can detect light, chemicals, and pressure with unprecedented precision. But the real breakthrough comes when some of these experimental organisms figure out how to coordinate the activities of millions of specialized cells into a single, unified body. We're talking about creatures that can grow to sizes measured in centimeters or even meters, with distinct body parts that perform completely different functions. This is the dawn of animal life, though these first animals are unlike anything walking the earth today. They're soft-bodied creatures that look more like living carpets or bizarre underwater plants than anything we'd recognize as an animal. Some are flat and circular, drifting through the water like biological frisbees. Others are elongated and segmented, crawling along the seafloor like primitive worms. Still others develop tentacles and feeding structures that make them look like alien flowers blooming in the deep ocean darkness. The most remarkable thing about these early animals isn't their appearance, though. It's their behavior. For the first time in Earth's history, we have organisms that can actively hunt, deliberately move from place to place, and make what can only be called decisions about how to respond to their environment. Watch one of these primitive hunters as it encounters potential prey. It doesn't just bump into its victim and hope for the best. It actually tracks the chemical trail left by its target, follows that trail through the water, and then uses specialized feeding structures to capture and consume its meal. This is intentional behavior, powered by the first nervous systems in Earth's history. These early nervous systems are incredibly simple by modern standards, just networks of interconnected cells that can pass electrical signals from one part of the body to another. But they represent a quantum leap in biological sophistication. For the first time, organisms can process information, store memories, and coordinate complex behaviors that involve their entire bodies. The implications of this neurological revolution extend far beyond individual organisms. Animals that can move deliberately and hunt actively create entirely new types of ecological pressure. They force other organisms to develop better defenses, more efficient escape mechanisms, and more sophisticated hiding strategies. This triggers an evolutionary arms race that accelerates the pace of innovation to levels that make everything we've seen so far look almost static. Over the course of just a few million years, a blink of an eye in geological terms, the oceans explode with new forms of life that display levels of complexity that seem to come out of nowhere. But here's the truly mind-blowing part of this story. All of this innovation is happening while the planet is still locked in one of the most severe ice ages in its history. Life isn't just surviving these brutal conditions, it's using them as a springboard for creativity that transforms the very nature of what living things can be and do. As the ice finally begins to retreat, around 635 million years ago, it reveals a world that has been completely transformed. The organisms that emerge from their frozen refuges aren't just survivors. They're pioneers carrying genetic innovations that will reshape every ecosystem on the planet. The retreat of the ice creates new opportunities for these experimental life forms to spread and diversify. As sea levels rise and new marine environments open up, animals begin to explore ecological niches that had never been occupied by complex organisms before. Some become filter feeders, creating the first biological water treatment plants that can clear vast volumes of seawater. Others become active predators, developing the first sophisticated hunting strategies in Earth's history. But perhaps the most significant development is the emergence of hard body parts. Some of these early animals begin to extract minerals from seawater and use them to build shells, spines, and other protective structures. This might seem like a minor innovation, but it has consequences that ripple through every aspect of planetary evolution. Hard body parts don't just provide protection, they create the first fossils that are detailed enough for us to study billions of years later. Suddenly, the fossil record explodes with evidence of animal life, giving us our first clear window into what these ancient ecosystems actually look like. More importantly, the evolution of biomineralization, the process of building hard structures from dissolved minerals, begins to alter the chemistry of the oceans themselves. Animals start extracting vast quantities of calcium, silica, and other minerals from seawater, incorporating them into their bodies and eventually depositing them on the seafloor when they die. This biological mining operation has profound effects on ocean chemistry and global climate. By removing greenhouse gases like carbon dioxide from the atmosphere and locking them away in limestone and other carbonate rocks, these early animals begin to influence global temperature in ways that no previous organisms ever could. As we move deeper into the Neoproterozoic era, the pace of change becomes almost dizzying. New animal body plans appear with increasing frequency, each more sophisticated than the last. Some develop the first true eyes, organs capable of forming images and detecting movement across significant distances. Others evolve complex digestive systems that allow them to process a much wider variety of food sources. But the most remarkable innovation during this period is the development of bilateral symmetry. Most of the earliest animals had been radially symmetric, like jellyfish or sea anemones, with body parts arranged in a circle around a central axis. But some lineages begin experimenting with bilateral symmetry, creating bodies with distinct front and back ends, left and right sides, and top and bottom surfaces. This might sound like a minor architectural detail, but bilateral symmetry enables a revolution in animal behavior and intelligence. Animals with front and back ends can move in a directed fashion, actively exploring their environment rather than just drifting with the currents. They can develop specialized sense organs at their front ends to gather information about where they're going. And they can evolve increasingly sophisticated brains to process all of this sensory information and coordinate increasingly complex behaviors. The emergence of bilateral symmetry sets the stage for one of the most spectacular episodes in the history of life on Earth. We're approaching the Cambrian period, an interval of time so rich in evolutionary innovation that paleontologists call it the Cambrian explosion. But before we get to that fireworks display of biological creativity, Earth has one more surprise to reveal. The solid planet beneath all of this biological innovation is undergoing changes that are just as dramatic as anything happening in the oceans. The breakup of the previous supercontinent is creating new patterns of ocean circulation, new climate zones, and new opportunities for both geological and biological processes. Massive mountain building episodes are exposing fresh rock surfaces to weathering and erosion, pumping new nutrients into the oceans and creating new terrestrial environments. Volcanic activity is introducing new chemical elements into both the atmosphere and the seas, providing raw materials for biological innovations that wouldn't have been possible before. The interaction between these geological changes and the biological revolution creates feedback loops that accelerate the pace of planetary evolution. More complex ecosystems alter patterns of sedimentation and erosion. New forms of biomineralization change the chemical composition of seawater. The emergence of large animals creates new types of bioturbation, the mixing of seafloor sediments by living organisms. All of these changes are building toward a crescendo that will transform Earth from a planet where life exists into a planet that is fundamentally shaped by life. We're approaching the moment when biology becomes geology, when living processes become so powerful that they rival volcanic eruptions and mountain building episodes as forces of planetary change. The stage is set for transformations that will make everything we've witnessed so far look like a gentle prelude to the main symphony. Complex ecosystems are about to emerge that rival modern coral reefs in their diversity and productivity. Predator-prey relationships are about to evolve that will drive the development of sophisticated sensory systems, rapid locomotion, and even primitive forms of intelligence. And for the first time in Earth's history, we're about to see organisms large enough and complex enough that if you could travel back in time, you would immediately recognize them as animals in the modern sense of the word. Not microscopic curiosities or strange bacterial mats, but creatures with eyes and mouths and bodies that move with clear intention through ancient seas. The story is accelerating toward revelations that will challenge everything we think we know about the relationship between simplicity and complexity, between chemistry and consciousness, between the possible and the actual. Earth is about to become not just a living planet, but a spectacular showcase for what evolution can accomplish when it's given enough time, enough space, and enough opportunities to experiment with the fundamental building blocks of existence. We're standing on the threshold of the visible world, the emergence of life forms, complex enough and large enough to be seen, studied, and appreciated by future observers who will marvel at the creativity embedded in every fossil, every ancient ecosystem, every layer of rock that preserves the memory of these remarkable transformations. The next chapter of this story will reveal how a planet of invisible microbes became a world where beauty, complexity, and intelligence could emerge from the patient work of natural selection operating across scales of time and space, that humble human imagination. We're about to witness the birth of the visible biosphere, and it's going to be more spectacular than anything we've imagined so far. The moment we've been building toward arrives with all the subtlety of a cosmic thunderclap. Around 541 million years ago, Earth's oceans explode into a festival of biological creativity, so spectacular, so unprecedented, that it redefines what it means to be alive on this planet. This is the Cambrian explosion, and it's not just an evolutionary event. It's a complete revolution in the nature of existence itself. Picture diving into these ancient seas and finding yourself surrounded by creatures that look like they were designed by an alien intelligence with an unlimited imagination and a twisted sense of humor. There's Opabinia, a five-eyed monster with a vacuum cleaner hose for a mouth. Wuaxia, covered in spines and scales like a medieval knight's armor. Hallucigenia, so bizarre that scientists initially reconstructed it upside down because they couldn't figure out which end was which. But here's what makes this explosion truly mind-blowing. These aren't just weird variations on familiar themes. These are completely new categories of life, experimental body plans that push the boundaries of what biological engineering can accomplish. Some of these creatures develop compound eyes with thousands of individual lenses, creating visual systems that won't be matched by human technology for hundreds of millions of years. Others evolve grasping appendages that can manipulate objects with precision, the first tools in Earth's history. Still others develop internal pumping systems that circulate fluids throughout their bodies, primitive hearts that will eventually evolve into the sophisticated cardiovascular systems of modern animals. The diversity is staggering. In a single square meter of Cambrian seafloor, you might find representatives of more major animal groups than exist in entire modern ecosystems. It's like evolution went on a creative binge, throwing every possible body plan at the wall to see what would stick. But this isn't random chaos. There's a method to this madness, driven by selective pressures that are unlike anything Earth has experienced before. The emergence of active predators creates what scientists call an evolutionary arms race, where every defensive innovation triggers a corresponding offensive adaptation. Prey animals develop the first sophisticated armor systems, shells and carapaces that can withstand crushing forces. Predators respond by evolving powerful claws, drilling apparatus, and chemical weapons that can penetrate these defenses. The result is an escalating cycle of innovation that drives complexity to unprecedented levels. Watch Anomalocaris, the ocean's first superpredator, as it glides through these ancient waters. This meter-long monster has flexible grasping arms that can pluck smaller animals from the sea floor, compound eyes that can track movement across vast distances, and a circular mouth lined with crushing plates that can process prey with mechanical efficiency. Its very existence forces every other animal in the ecosystem to adapt or die. Some develop better escape mechanisms, learning to dart and weave through the water in unpredictable patterns. Others retreat into heavily fortified shells, turning themselves into biological tanks. Still others develop the first sophisticated camouflage systems, chemical and visual tricks that make them nearly invisible to hunting predators. But perhaps the most remarkable adaptation is the evolution of collective behavior. Some of these early animals begin working together in ways that multiply their individual capabilities. They form hunting packs, coordinate their movements, and even develop primitive communication systems that allow them to share information about food sources and dangers. This social revolution has implications that extend far beyond hunting strategies. Animals that can cooperate effectively begin to engineer their environments on scales that dwarf anything achieved by their predecessors. They build the first complex reefs, underwater cities that create their own local climates, and support thousands of different species. These Cambrian reef systems are architectural marvels that rival anything constructed by modern marine organisms. They create three-dimensional habitats with multiple levels, specialized neighborhoods for different types of creatures, and sophisticated water circulation systems that maintain optimal conditions throughout the structure. More importantly, these reef ecosystems begin to influence global climate and ocean chemistry in ways that make their builders active participants in planetary evolution. They extract enormous quantities of carbon dioxide from seawater, locking it away in limestone structures that will persist for hundreds of millions of years. Meanwhile, the solid Earth is undergoing equally dramatic transformations. The continents that had been relatively stable for hundreds of millions of years begin moving in new patterns, driven by changes in the planet's interior that we're only beginning to understand. These continental movements create new ocean basins, new mountain ranges, and new patterns of climate and weather that provide fresh opportunities for biological innovation. Shallow seas extend across vast areas of the continents, creating marine environments that are perfect laboratories for evolutionary experimentation. But the most significant change during this period involves the relationship between life and the physical environment. For the first time in Earth's history, biological processes become powerful enough to compete with geological forces in shaping the planet's surface. Animals burrowing through seafloor sediments create the first complex bioturbation systems, mixing and aerating marine substrates in ways that fundamentally alter ocean chemistry. Filter-feeding organisms process such enormous volumes of seawater that they begin to influence the clarity and chemical composition of entire ocean basins. Perhaps most remarkably, some of these early animals begin to actively modify their environments to make them more suitable for their own needs. They're not just adapting to existing conditions anymore, they're becoming ecosystem engineers, creating new types of habitats that didn't exist before. The implications of this transition are staggering. Life is no longer just a passenger on spaceship Earth. It's become a member of the crew, actively participating in planetary management in ways that will continue to evolve for the next 500 million years. As we move deeper into the Cambrian period, the pace of innovation continues to accelerate. New sensory systems appear that can detect vibrations, chemical gradients, electrical fields, and even magnetic orientation. Some animals develop the first sophisticated locomotion systems, internal skeletons that provide structural support for rapid, directed movement. Others evolve complex digestive systems that allow them to process previously inedible food sources, opening up entirely new ecological niches. The first true jaws appear, mechanical structures that can crack shells, tear flesh, and process plant material with unprecedented efficiency. But perhaps the most significant development is the emergence of the first centralized nervous systems. Some of these Cambrian animals develop brain-like structures that can integrate information from multiple sensory organs, store memories of past experiences, and coordinate complex behaviors that involve their entire bodies. These early brains are incredibly simple by modern standards, just clusters of nerve cells that process basic sensory information and control motor functions. But they represent a quantum leap in biological sophistication. The first information processing systems capable of what we might recognize as primitive intelligence. The animals that possess these early brains begin to exhibit behaviors that suggest they can learn from experience, recognize individual members of their own species, and even solve simple problems that require multiple steps to complete. They're not just reacting to their environment anymore, they're beginning to understand it. This cognitive revolution creates new types of ecological relationships that go far beyond simple predator-prey dynamics. Animals begin to form social hierarchies, engage in complex mating rituals, and even develop primitive forms of parental care that increase the survival chances of their offspring. The emergence of these sophisticated behaviors transforms the nature of natural selection itself. Instead of just selecting for physical traits like size, speed, or armor thickness, evolution begins to favor intelligence, learning ability, and behavioral flexibility. Animals that can adapt their behavior to changing circumstances gain enormous advantages over their more rigid competitors. They can exploit new food sources, avoid novel dangers, and take advantage of unexpected opportunities in ways that purely instinct-driven organisms cannot match. This behavioral arms race accelerates the evolution of sensory systems, information processing capabilities, and motor control mechanisms. The animals that survive and thrive are those that can gather the most information about their environment, process that information most effectively, and respond with the greatest speed and precision. As the Cambrian explosion reaches its peak, Earth's oceans contain ecosystems of such complexity and diversity that they won't be matched again for hundreds of millions of years. Every major animal group that exists today can trace its ancestry back to this remarkable period, along with dozens of experimental lineages that tried alternative approaches to the challenges of complex multicellular life. But this explosion of creativity comes at a cost. The intense competition and rapid environmental changes that drive innovation also create instability that makes survival increasingly precarious. Many of the most spectacular Cambrian experiments in body plan design turn out to be evolutionary dead ends, beautiful solutions to problems that turn out to be temporary. As we approach the end of the Cambrian million years ago Earth period, around 485's marine ecosystems are poised for a major reorganization. The experimental phase of animal evolution is coming to an end, replaced by a more stable period where successful body plans become refined and optimized rather than completely reinvented. But the legacy of the Cambrian explosion extends far beyond the fossil record. This period establishes the basic architectural principles that will guide animal evolution for the rest of Earth's history. The sensory systems, nervous systems, and behavioral capabilities that emerged during this time provide the foundation for everything that follows. More importantly, The Cambrian explosion demonstrates that evolution is capable of creativity that seems to border on the miraculous. In just a few million years, natural selection transforms simple colonial organisms into complex animals with sophisticated sensory systems, advanced behavioral capabilities, and the beginnings of what we might recognize as intelligence. This transformation reveals something profound about the nature of complexity itself. Given the right conditions, the right raw materials, and enough time for experimentation, simple systems can give rise to emergent properties that seem to transcend their humble origins. The animals swimming through Cambrian seas carry within their nervous systems the seeds of consciousness, creativity, and curiosity that will eventually allow their distant descendants to contemplate their own origins and wonder about their place in the cosmic story. We're witnessing the birth of awareness itself, the first tentative steps towards the kind of self-reflective intelligence that makes it possible for matter to understand matter, for the universe to contemplate its own existence through the evolved consciousness of living beings. But we're still hundreds of millions of years away from creatures sophisticated enough to ask these kinds of questions. The journey from these early Cambrian pioneers to the emergence of human consciousness will require innovations in neural architecture, social organization, and cultural evolution that make everything we've seen so far look like a preliminary sketch. Yet the fundamental breakthrough has already occurred. Life has learned to process information, store memories, and make decisions based on past experience. The hardware of intelligence is in place, even if the software is still incredibly primitive. As Earth moves beyond the Cambrian explosion into the next chapter of its evolutionary story, the stage is set for transformations that will make the oceans just one theatre in a much larger drama. Life is about to discover the land, that vast frontier that has remained almost completely unexplored throughout the entire history of complex organisms. The colonization of terrestrial environments will require innovations that make the Cambrian explosion look conservative by comparison. Animals and plants will need to develop new ways of obtaining oxygen, new methods of reproduction, new strategies for dealing with gravity and temperature extremes. But first, they'll need to solve the most basic challenge of all: how to survive in a world without water. The colonization of land represents one of the most audacious experiments in the history of life, a venture so bold that it requires reinventing almost every aspect of how organisms function. Picture the challenge these early pioneers faced. After spending over 3 billion years perfecting life in water, evolution now had to solve problems that had never existed before. Water provides structural support, carries nutrients directly to cells, facilitates reproduction, and maintains constant temperatures. On land, organisms would need to develop their own structural frameworks, create internal transportation systems, invent new reproductive strategies, and cope with temperature swings that could kill them within hours. The first tentative steps toward terrestrial life begin in the shallow margins where water meets land. These aren't dramatic conquests, but subtle experiments in survival at the very edge of habitability. Simple organisms like algae and bacteria begin forming thin films on rocks near the water's edge, testing their ability to survive brief periods of exposure to air. These pioneer communities face challenges that push the boundaries of biological engineering. Without water to support their bodies, they must develop new ways to maintain their shape and structure. Without the constant flow of nutrients that water provides, they must create systems for storing and distributing resources internally. Most critically, they must prevent themselves from drying out completely, a process that would destroy their cellular machinery within minutes. The solutions these early terrestrial organisms develop are masterpieces of biological innovation. They create waxy coatings that reduce water loss while still allowing gas exchange. They develop internal water storage systems that can sustain them through dry periods. Some even evolve the ability to enter dormant states, essentially shutting down all non-essential life processes until conditions improve. But the real breakthrough comes when some of these organisms discover how to extract resources directly from rock and soil. Instead of relying entirely on nutrients dissolved in water, they begin breaking down mineral substrates chemically, essentially eating the planet itself. This innovation opens up vast new territories for biological colonization. As these pioneering communities become more established, they begin to modify their terrestrial environments in ways that make them more hospitable for other organisms. They create soil by breaking down rock and organic matter. They provide shelter and moisture retention that other species can exploit. They even begin to influence local weather patterns through their effects on evaporation and temperature. The success of these early terrestrial experiments attracts more complex organisms from the marine realm. Some of the smaller animals that had evolved in shallow water environments begin making brief forays onto land, initially just to escape predators or access new food sources. These early terrestrial animals face even greater challenges than the pioneering plants and microbes. Animals have higher energy requirements, more complex internal systems, and greater sensitivity to environmental conditions. Moving onto land requires solving problems in structural engineering, respiratory physiology, and sensory adaptation that push evolution to new levels of creativity. The first animal colonists developed primitive air-breathing systems, modifications of gills that can extract oxygen from the atmosphere rather than from water. They create rudimentary limbs that can support their body weight against gravity, replacing the fins and swimming appendages that worked perfectly in aquatic environments. Perhaps most remarkably, they begin to develop new sensory systems adapted to terrestrial conditions. Vision becomes far more important in the bright, clear air above water. Sound travels differently through air than through water, requiring new types of hearing organs. Chemical detection, so crucial for finding food and mates, requires completely different approaches when dealing with airborne molecules rather than dissolved substances. But the most profound challenge these early terrestrial animals face involves reproduction. In water, organisms can simply release eggs and sperm into the surrounding medium, relying on currents and chance encounters for fertilization. On land, this strategy leads to immediate death by dehydration. The solutions evolution develops to this reproductive challenge are among the most elegant in the entire history of life. Some organisms develop internal fertilization systems that protect reproductive cells from desiccation. Others create protective shells around their eggs that can resist drying out while still allowing gas exchange. Still others evolve complex mating behaviors that ensure reproductive success in this harsh new environment. As terrestrial ecosystems become more established, they begin to support increasingly complex food webs. The first terrestrial plants develop sophisticated root systems that can extract water and nutrients from deep within the soil. They create structural tissues that allow them to grow tall, competing for sunlight in ways that would be impossible in aquatic environments. These early forests transform the terrestrial landscape in ways that create entirely new opportunities for animal life. They provide three-dimensional habitat structures that animals can exploit in countless ways. They create microenvironments with different temperature, humidity, and light conditions. They produce new types of food resources that terrestrial animals can learn to exploit. The animals that colonize these early forests undergo rapid evolutionary changes that seem to happen almost in real time by geological standards. Some develop the ability to climb, creating the first arboreal ecosystems. Others become specialized for digging, exploiting the rich underground environment that plant roots have created. Still others learn to fly, opening up the three-dimensional aerial environment that had remained completely unexplored throughout the entire history of complex life. The evolution of flight represents perhaps the most spectacular innovation in terrestrial animal evolution. The first flying animals aren't birds, but insects, arthropods, that solve the engineering challenges of powered flight using completely different principles than any vertebrate will ever discover. These early flying insects transform terrestrial ecosystems in ways that ripple through every aspect of life on land. They become pollinators, creating new types of relationships between plants that revolutionize terrestrial reproduction. They become aerial predators, creating new selective pressures that drive the evolution of defensive strategies in ground-dwelling animals. They even become long-distance dispersal agents, carrying genetic material between isolated populations in ways that accelerate the pace of evolutionary change. Meanwhile, the colonization of land is having profound effects on global climate and ocean chemistry. Terrestrial plants begin extracting enormous quantities of carbon dioxide from the atmosphere, using it to build their bodies, and eventually burying it in soils and sediments. This biological carbon sequestration starts to influence global temperature in ways that marine organisms never could. The weathering of rocks by plant roots and soil organisms accelerates the breakdown of continental surfaces, pumping new nutrients into river systems and ultimately into the oceans. This enhanced nutrient flow triggers productivity booms in marine ecosystems that support larger and more diverse animal communities. But perhaps the most significant change involves the water cycle itself. Terrestrial plants begin to influence patterns of evaporation, precipitation, and water retention in ways that create entirely new climate zones. They stabilize soil that would otherwise be eroded away by wind and rain. They create local weather systems that can influence temperature and humidity across vast areas. As terrestrial ecosystems mature, they begin to support animal communities of unprecedented complexity. The first terrestrial vertebrates evolved from fish that had developed primitive air-breathing capabilities, initially as adaptations for surviving in oxygen-poor water environments. These early terrestrial vertebrates are still closely tied to aquatic environments, requiring water for reproduction and spending much of their time in ponds and streams. But they represent a crucial evolutionary bridge between fully aquatic and fully terrestrial ways of life. The transition from aquatic to terrestrial vertebrates requires innovations that rival anything we've seen in the entire history of life. These animals must develop new types of skeletons that can support their body weight against gravity. They must create new respiratory systems that can extract oxygen efficiently from air rather than water. They must evolve new sensory systems adapted to terrestrial conditions. But perhaps most importantly, they must develop new reproductive strategies that can function in terrestrial environments. The evolution of the amniotic egg, a self-contained life support system that allows vertebrates to reproduce without returning to water, represents one of the most crucial innovations in the history of terrestrial life. This reproductive breakthrough frees vertebrates from their dependence on aquatic environments and allows them to colonize the vast terrestrial territories that had remained largely unexplored. The descendants of these early amniotes will eventually give rise to reptiles, birds, and mammals, the vertebrate groups that will dominate terrestrial ecosystems for the next 300 million years. As we move deeper into this terrestrial revolution, the pace of evolutionary innovation continues to accelerate. New ecological relationships develop between plants and animals that create feedback loops of increasing complexity. Herbivorous animals evolve more efficient digestive systems that allow them to exploit plant resources more effectively. Plants respond by developing new defensive chemicals and physical structures that protect them from herbivory. Predatory animals develop increasingly sophisticated hunting strategies that take advantage of the three-dimensional structure of terrestrial environments. They learn to use cover and concealment, to coordinate group hunting behaviors, and to exploit the predictable movement patterns of their prey. But the most remarkable development during this period is the emergence of increasingly complex nervous systems that can process the rich sensory information available in terrestrial environments. The brains of terrestrial animals begin to show levels of complexity that dwarf anything seen in their aquatic ancestors. These enhanced nervous systems enable new types of behaviors that seem to border on intelligence. Animals begin to show evidence of learning, memory, and even primitive problem-solving abilities that allow them to adapt to changing environmental conditions. The cognitive capabilities of these early terrestrial animals create new types of ecological relationships that go beyond simple predator-prey interactions. Some species begin to form social groups with complex hierarchical structures. Others develop sophisticated communication systems that allow them to share information about food sources, dangers, and reproductive opportunities. Perhaps most remarkably, some terrestrial animals begin to modify their environments in ways that seem to show planning and foresight. They build shelters, create food storage systems, and even engage in primitive forms of agriculture that increase their local food supply. These behavioral innovations represent the first tentative steps toward the kind of environmental manipulation that will eventually characterize human civilization. But we're still hundreds of millions of years away from that level of sophistication. As Earth's terrestrial ecosystems continue to evolve and mature, they create opportunities for innovations that will make everything we've seen so far look like preliminary experiments. The stage is being set for the emergence of warm-blooded animals that can maintain constant body temperatures, allowing them to remain active in a much wider range of environmental conditions. The evolution of endothermy will enable animals to colonize environments that had been inaccessible to their cold-blooded predecessors. They'll altitudes and other be able to survive in polar regions, high extreme environments that had remained largely lifeless throughout the entire history of complex organisms. But perhaps more importantly, the high metabolic rates required for endothermy will enable the evolution of larger, more complex brains that can support sophisticated cognitive abilities. The energy-intensive nature of neural tissue means that only warm-blooded animals will be able to afford the metabolic costs of true intelligence. We're approaching one of the most dramatic transitions in Earth's history. The emergence of animals sophisticated enough to be aware of their own awareness, to contemplate their own existence, and to actively modify their environment on a scale that rivals geological processes. The story is building toward the appearance of consciousness itself, that mysterious property that allows matter to contemplate matter, allows the universe to become aware of its own existence through the evolved intelligence of living beings. But before we get to that extraordinary development, Earth has several more surprises in store. The planet is about to experience climate changes, mass extinctions, and evolutionary innovations that will test life's resilience in ways we haven't yet imagined. The terrestrial world that emerges from these future challenges will be recognizably similar to the modern Earth, with forests, grasslands, and animal communities that wouldn't seem completely alien to a modern observer. Yet the journey from these early terrestrial pioneers to the complex ecosystems of today will require innovations in physiology, behavior, and intelligence that represent some of the most remarkable achievements in the entire history of evolution. The transformation we're witnessing represents more than just biological colonization. It's the emergence of planetary intelligence, scattered across countless individual organisms, but beginning to function as something approaching a global nervous system. These early terrestrial communities are developing feedback mechanisms that allow them to respond to environmental changes with increasing sophistication. Picture the interconnected web of chemical signals that now flows through soil systems. Plant roots release compounds that attract beneficial microorganisms while repelling harmful ones. Mycorrhizal fungi create underground networks that span entire forests, sharing nutrients and information between plants that may be kilometers apart. These fungal highways carry chemical messages about drought conditions, pest attacks, and resource availability with a speed and efficiency that rivals modern communication systems. But the real breakthrough comes when these terrestrial ecosystems begin to influence their own climate. Forests don't just respond to rainfall patterns, they create them. Trees pump water vapor into the atmosphere through their leaves, generating the humidity needed for cloud formation. Their canopies intercept solar radiation, creating cooler microclimates that extend far beyond the forest boundaries. This biological climate control represents a quantum leap in the sophistication of Earth's self-regulation systems. For the first time in the planet's history, living organisms are actively managing atmospheric conditions on a continental scale. They're not just adapting to their environment anymore, they're designing it. The implications extend far beyond local weather patterns. These terrestrial carbon pumps begin extracting atmospheric carbon dioxide at rates that dwarf anything achieved by marine organisms. Every tree that grows, every leaf that photosynthesis, every root system that extends deeper into the soil is participating in a massive planetary experiment in atmospheric engineering. As carbon dioxide levels drop, global temperatures begin to shift in ways that create entirely new climate zones. Ice caps expand and contract in response to these biological influences. Ocean currents reorganize around new temperature gradients. Weather patterns that had been stable for hundreds of millions of years begin to fluctuate in response to the growing influence of terrestrial life. But here's where the story takes one of its most dramatic turns. The success of terrestrial ecosystems creates conditions that trigger one of the most severe environmental crises in Earth's history. As forests spread across the continents, they extract so much carbon dioxide from the atmosphere that global temperatures plummet into another ice age. This isn't just a cold snap. This is a freeze event so severe that it threatens to undo hundreds of millions of years of evolutionary progress. Glaciers advance from the poles toward the equator, locking up vast quantities of water and dropping sea levels by hundreds of meters. Marine ecosystems that had thrived in warm, shallow seas find themselves stranded in deep, cold basins where photosynthesis becomes almost impossible. The terrestrial organisms that triggered this crisis face their own existential challenges. Many of the forests that had seemed so successful begin to die back as temperatures drop below their tolerance limits. The delicate balance between carbon extraction and temperature regulation breaks down, creating feedback loops that threaten to spiral out of control. Yet once again, life demonstrates its extraordinary capacity for innovation under pressure. The organisms that survive this climatological catastrophe emerge with capabilities that seem to transcend the limitations that had constrained their predecessors. plants develop new forms of cold tolerance that allow them to photosynthesize even under near-freezing conditions. Animals evolve more sophisticated behavioral strategies for dealing with seasonal temperature swings. But the most remarkable adaptation involves the evolution of endothermy, the ability to generate internal heat through metabolic processes. This innovation allows animals to maintain constant body temperatures regardless of environmental conditions, effectively making them independent of external climate fluctuations. The emergence of warm-blooded animals represents one of the most energy-expensive innovations in the history of life. Maintaining constant internal temperatures requires metabolic rates that are 5 to 10 times higher than those of cold-blooded animals. This means endothermic organisms need vastly more food, more efficient digestive systems, and more sophisticated cardiovascular networks to fuel their internal furnaces. But the benefits are extraordinary. Warm-blooded animals can remain active in environments that would shut down their cold-blooded competitors. They can hunt at night when temperatures drop. They can colonize high-altitude environments where temperature swings would be lethal to other organisms. Most importantly, they can maintain the high metabolic rates needed to support large, complex brains. This neurological revolution enables cognitive capabilities that blur the line between instinct and intelligence. These early endothermic animals begin to exhibit behaviors that suggest they can form mental models of their environment, predict future events based on past experience, and even engage in what appears to be creative problem-solving. Watch a pack of these early mammalian predators as they coordinate a hunt. They don't just chase their prey in a straight line. They anticipate where their target is going, position themselves to cut off escape routes, and adjust their strategy in real time based on their prey's responses. This requires a level of cognitive sophistication that seems to approach genuine understanding. The social implications of these enhanced cognitive abilities are equally remarkable. Animals with larger brains begin to form more complex social structures, with hierarchies based not just on size and strength, but on intelligence, experience, and social alliances. They develop communication systems that can convey abstract information about things that aren't immediately present. Some of these early social mammals begin to exhibit behaviors that seem to show empathy, cooperation that goes beyond immediate self-interest, and even primitive forms of cultural transmission, where knowledge gets passed from one generation to the next through learning rather than genetic inheritance. But perhaps the most significant development is the emergence of animals that seem to be aware of their own awareness. These creatures don't just respond to their environment, they appear to contemplate it. They show evidence of curiosity about things that have no immediate survival value. They engage in play behaviors that seem to exist purely for the joy of exploration and discovery. This cognitive revolution coincides with another dramatic shift in Earth's physical systems. The ice age that had dominated the planet for millions of years finally begins to retreat. But the world that emerges is fundamentally different from anything that came before. The climate is more dynamic, with seasonal variations that create new opportunities for biological innovation. The retreat of the ice reveals landscapes that have been sculpted by millions of years of glacial activity. Vast river systems carry meltwater across continents, creating new wetland habitats and marine environments. Mountain ranges that had been buried under ice emerge as islands of unique climate conditions that support endemic species found nowhere else on Earth. These diverse new environments become laboratories for evolutionary experimentation on a scale that dwarfs even the Cambrian explosion. Animals begin to specialize for specific ecological niches with unprecedented precision. Some become adapted for life in dense forests, developing enhanced climbing abilities and sophisticated three-dimensional navigation skills. Others specialize for open grasslands, evolving speed and endurance capabilities that allow them to cover vast distances in search of resources. But the most remarkable adaptations involve animals that learn to exploit the boundary zones between different environments. These ecological generalists develop behavioral flexibility that allows them to switch between different survival strategies depending on local conditions. They become the first true problem solvers, animals that can assess novel situations and develop creative solutions in real time. The success of these cognitively advanced animals creates new selective pressures that accelerate the evolution of intelligence throughout terrestrial ecosystems. Animals that can learn faster, remember more information, and solve more complex problems gain enormous advantages over their less flexible competitors. This creates an evolutionary arms race focused on cognitive capabilities rather than just physical traits. Predators develop more sophisticated hunting strategies that require their prey to evolve better escape tactics and predator detection systems. Social animals develop more complex communication systems that allow them to coordinate increasingly elaborate group behaviors. The result is an explosion in brain size and neural complexity that transforms the nature of animal behavior. These enhanced nervous systems enable animals to engage in activities that seem to have no immediate survival function, but appear to exist purely for the pleasure of mental stimulation. Some animals begin to engage in tool use, manipulating objects in their environment to achieve goals that would be impossible with their natural anatomy alone. Others develop artistic behaviors, creating structures and patterns that seem to serve no function other than aesthetic expression. Still others exhibit what can only be called scientific curiosity, systematically exploring their environment and experimenting with cause and effect relationships. As we move deeper into this age of cognitive evolution, the boundary between animal behavior and what we might recognize as primitive culture begins to blur. Some species develop traditions that get passed down through generations, accumulating knowledge and behavioral innovations that exceed what any individual could discover in a single lifetime. These proto-cultural systems create feedback loops that accelerate the pace of behavioral evolution far beyond what genetic mechanisms alone could achieve. Animals can now adapt to new environmental challenges within a single generation by learning new behaviors from their peers, rather than waiting for favorable mutations to spread through the population. The implications of this cultural revolution extend far beyond individual species. Animals that can share information and coordinate their activities begin to modify their environments in ways that seem to show planning and foresight. They create structures that persist beyond their own lifetimes, alter local ecosystems to increase their productivity, and even engage in what appears to be primitive forms of resource management. But we're still millions of years away from the emergence of animals sophisticated enough to contemplate their own existence in any philosophical sense. The journey from these early cognitive pioneers to truly self-aware consciousness will require innovations in neural architecture, social organization, and symbolic communication that represent some of the most remarkable achievements in evolutionary history. Yet the foundation has been established. The hardware of intelligence is in place, continuously being refined and expanded through the relentless pressure of cognitive competition. The software of culture has begun to emerge, creating new mechanisms for storing and transmitting information across generations. As Earth moves toward its next great transformation, the stage is set for the emergence of animals that won't just adapt to their environment, but will actively reshape it on a planetary scale. The story is building toward the appearance of consciousness, sophisticated enough to recognize its own place in the cosmic narrative, to ask questions about its own origins, and to wonder about its ultimate destiny. The dance between geology and biology, between planetary processes and living systems, is approaching a crescendo that will transform Earth from a world where intelligence exists into a world that is actively shaped by intelligence. We're witnessing the emergence of the first stirrings of what will eventually become technological civilization, though that extraordinary development is still far in the future. For now, we can marvel at the patient work of evolution as it constructs increasingly sophisticated information processing systems, behavioral repertoires, and social structures that point toward possibilities we're only beginning to imagine. The story of Earth's evolution is becoming a story about the evolution of mind itself, about the universe's apparent drive towards self-awareness through the emergence of consciousness in living beings. The transformation we're witnessing now represents something unprecedented in the entire history of our planet. For billions of years, evolution has been crafting increasingly sophisticated biological machines, but something fundamentally different is beginning to emerge from this ancient process. We're approaching the threshold where life doesn't just respond to its environment or even modify it, but begins to understand it in ways that transcend anything we've seen before. Picture the world as it exists roughly 65 million years ago, just after one of the most catastrophic events in Earth's history has reshaped the entire planetary ecosystem. A massive asteroid impact has wiped out the dominant reptilian giants that had ruled terrestrial environments for over 160 million years. The skies have cleared from the debris and ash that had blocked out the sun for months, and life is beginning to experiment with possibilities that had been foreclosed for eons. Into this vacant ecological landscape step the descendants of those early endothermic pioneers we encountered earlier. These are small, warm-blooded creatures with brains that seem disproportionately large for their body size. They've survived the Great Catastrophe by being adaptable rather than specialized, intelligent rather than simply powerful, cooperative rather than merely competitive. What happens next unfolds like a biological explosion in slow motion, but the innovations that emerge will make the Cambrian explosion look like a gentle rehearsal for the main performance. These surviving mammals don't just fill the empty ecological niches left by their extinct predecessors. They reinvent what it means to be a complex organism on this planet. The most remarkable changes begin in their nervous systems. Generation by generation, these post-catastrophe mammals develop brains with new types of neural architecture that can process information in fundamentally different ways. They're not just getting bigger brains, they're developing qualitatively different kinds of cognitive machinery. Some lineages begin to show evidence of what can only be called imagination. They demonstrate the ability to mentally simulate scenarios that haven't happened yet, to plan for future events that exist only as possibilities in their minds. Watch a group of early primates as they navigate through a complex forest canopy. They're not just reacting to immediate obstacles and opportunities. They're thinking several moves ahead, choosing routes that will position them optimally for challenges they haven't encountered yet. This capacity for mental simulation enables entirely new categories of behavior. Animals can now engage in what appears to be genuine experimentation, systematically testing different approaches to problems and learning from the results. They begin to develop what we might recognize as scientific thinking, forming hypotheses about how their world works, and then testing those hypotheses through deliberate action. But the real breakthrough comes when some of these cognitively advanced mammals discover that they can manipulate not just physical objects, but information itself. They develop the ability to create and manipulate symbols, abstract representations that can stand for things that aren't immediately present. The emergence of symbolic thinking represents one of the most profound innovations in the entire history of life on Earth. For the first time, organisms can think about things that exist only as ideas. They can communicate about past events, future possibilities, and abstract concepts that have no physical existence. This symbolic revolution transforms the nature of social interaction in ways that ripple through every aspect of these animals' lives. They begin to develop complex cultural systems where knowledge, traditions, and innovations can be preserved and transmitted across generations with unprecedented fidelity. Some groups develop elaborate communication systems that allow them to share detailed information about their environment, their experiences, and even their thoughts and feelings. These aren't just warning calls or mating displays. These are genuine conversations where individuals exchange complex information and build upon each other's ideas. The cultural evolution that emerges from these enhanced communication abilities begins to operate on timescales that dwarf biological evolution. Instead of waiting millions of years for beneficial mutations to spread through populations, these animals can now adapt to new challenges within a single generation by developing new cultural practices and sharing them throughout their communities. Watch as one group discovers a new technique for obtaining food or avoiding predators. Within days or weeks, this innovation spreads throughout the entire population. Within a few generations, it becomes so deeply embedded in their cultural practices that it seems like an instinctive behavior. But unlike true instincts, these cultural innovations can be modified, improved, and combined with other innovations to create increasingly sophisticated behavioral repertoires. This acceleration in the pace of adaptation creates feedback loops that drive the evolution of even more sophisticated cognitive capabilities. Animals that can learn faster, remember more information, and share their discoveries more effectively gain enormous advantages over their competitors. The result is an evolutionary arms race focused entirely on intelligence, creativity, and cultural sophistication. Brain sizes begin to increase at rates that seem almost impossible by normal evolutionary standards. Neural complexity expands in ways that create entirely new categories of mental capability. Some lineages develop the ability to recognize themselves in reflections, demonstrating a level of self-awareness that suggests they understand their own existence as distinct entities in the world. Others begin to show evidence of empathy so sophisticated that they can understand and respond to the mental states of other individuals, even when those states are quite different from their own immediate experience. But perhaps the most remarkable development is the emergence of animals that seem to be aware of their own awareness. They don't just think, they think about thinking. They don't just solve problems, they contemplate the nature of problem solving itself. These metacognitive abilities enable entirely new categories of behavior that seem to transcend the normal boundaries of animal intelligence. Some individuals begin to engage in activities that appear to have no survival function whatsoever, but seem to exist purely for the intellectual pleasure of exploration and discovery. They investigate objects and phenomena that have no immediate relevance to their survival needs. They experiment with cause and effect relationships that don't directly benefit them. They even begin to create aesthetic displays that seem to serve no function other than the expression of creativity and the appreciation of beauty. As these cognitively advanced mammals continue to evolve, they begin to modify their environments in ways that go far beyond anything we've seen in the entire history of life. They don't just build shelters, they engineer entire landscapes to suit their needs. They don't just gather food, they actively manage ecosystems to increase their productivity. Some groups develop what can only be called primitive technology, creating tools that extend their physical capabilities and allow them to manipulate their environment in ways that would be impossible with their natural anatomy alone. These tools aren't just simple implements like the sticks and stones used by their predecessors. They're complex devices that require sophisticated understanding of physics, materials science, and engineering principles. More remarkably, these technological innovations begin to accumulate and improve across generations. Each generation inherits the tools and techniques developed by their predecessors and then adds their own innovations to the mix. This creates a ratchet effect where technological complexity increases steadily over time, with each generation building upon the achievements of those who came before. The implications of this technological evolution extend far beyond the immediate benefits of better tools and techniques. The process of creating and improving technology requires forms of abstract thinking that push cognitive evolution in entirely new directions. Animals that engage in technological innovation must be able to envision objects and systems that don't yet exist. They must understand abstract principles like leverage, aerodynamics, and thermodynamics well enough to apply them in practical situations. They must be able to plan complex projects that require coordinated effort from multiple individuals over extended periods of time. These technological challenges drive the evolution of cognitive capabilities that seem to approach genuine intelligence in the human sense of the word. The animals that excel at technological innovation develop enhanced abilities in spatial reasoning, causal understanding, and abstract problem solving that set them apart from all their predecessors. But the most significant change involves their relationship with information itself. These technologically sophisticated animals begin to develop external storage systems for knowledge and cultural information. They create physical objects that can preserve and transmit complex information across time and space. Some groups develop primitive forms of symbolic notation that allow them to record information about their environment, their experiences, and their discoveries. These aren't just simple markers or memory aids. They're genuine information storage systems that can preserve complex knowledge independently of any individual's memory. The emergence of external information storage represents a quantum leap in the sophistication of cultural evolution. Instead of being limited by the memory capacity of individual brains, these animals can now accumulate knowledge indefinitely. Cultural innovations that might otherwise be lost when their creators die can now be preserved and built upon by future generations. This creates exponential growth in the complexity and sophistication of cultural systems. Each generation inherits not just the biological capabilities developed through millions of years of evolution, but also the accumulated cultural knowledge of all previous generations. The result is a form of superorganic evolution that operates at speeds that dwarf anything seen in purely biological systems. As we move deeper into this age of accelerating cultural evolution, the boundary between animal behavior and what we might recognize as primitive civilization begins to blur completely. These cognitively advanced mammals begin to develop social institutions that can coordinate the activities of thousands of individuals across vast geographic areas. They create systems of governance that can maintain social order and cooperation on scales that exceed anything possible through simple dominance hierarchies. They develop economic systems that can efficiently allocate resources and coordinate complex projects requiring specialized skills and extensive cooperation. Most remarkably, they begin to develop what can only be called scientific thinking on a cultural scale. Instead of relying on individual trial and error learning, they create systematic methods for investigating their world, testing hypotheses, and accumulating reliable knowledge about natural phenomena. These proto-scientific cultures begin to develop increasingly accurate models of how their world works. They figure out the relationships between astronomical events and seasonal changes. They discover principles of engineering that allow them to build increasingly sophisticated structures and machines. They even begin to understand biological processes well enough to actively manage and improve their food sources. But perhaps the most profound development is their growing awareness of their own place in the natural world. These intelligent animals begin to ask questions that transcend immediate practical concerns. They wonder about their own origins, their relationship to other forms of life, and their place in the larger cosmic order. This philosophical awakening represents the emergence of something unprecedented in the history of our planet. For the first time, Earth has given rise to organisms that can contemplate their own existence, question their own nature, and actively seek to understand the world that created them. We're witnessing the birth of consciousness in the deepest sense of that word, not just awareness or intelligence or even self-awareness, but the kind of reflective consciousness that can step outside immediate experience and contemplate the nature of existence itself. These philosophically inclined mammals begin to develop increasingly sophisticated models of their own minds and the minds of others. They recognize that different individuals can have different beliefs, desires, and perspectives. They understand that knowledge can be incomplete or incorrect, and that systematic investigation is required to distinguish truth from error. This metacognitive revolution enables forms of cooperation and cultural development that seem to transcend the normal limitations of biological evolution. Groups that can accurately model each other's mental states can coordinate their activities with unprecedented precision. They can share complex information, plan elaborate joint projects, and even engage in forms of collective problem solving that exceed the capabilities of any individual. The social implications of these enhanced cognitive abilities are staggering. These animals begin to form communities that can persist and grow across multiple generations, accumulating knowledge, resources, and cultural innovations that make them increasingly powerful relative to their environment. But with this growing power comes a new kind of responsibility. For the first time in Earth's history, we have organisms that are consciously aware of their impact on their environment and capable of making deliberate choices about how to exercise their influence. The story is building toward a transformation that will make everything we've witnessed so far look like a prologue to the main event. We're approaching the emergence of animals so cognitively sophisticated that they can actively reshape their planet on a geological scale, not through unconscious biological processes, but through conscious, deliberate technological intervention. The dance between mind and matter, between consciousness and cosmos, is approaching a crescendo that will transform Earth from a world where intelligence exists into a world that is actively designed by intelligence. The patient work of evolution is giving rise to something that transcends evolution itself, the emergence of conscious agents capable of directing their own development and actively participating in the continued creation of their world. But here's where our story reaches its most extraordinary crescendo. These conscious beings don't just observe the world around them. They begin to actively participate in the ongoing evolution of their planet in ways that blur the line between natural processes and deliberate design. What emerges is something that has never existed before in the 4.5 billion year history of our planet. Organisms capable of conscious planetary stewardship. Picture these remarkable creatures as they develop increasingly sophisticated understanding of the interconnected systems that sustain their world. They begin to recognize that the atmosphere they breathe, the water they drink, and the soil that grows their food are all part of a delicate web of relationships that extends far beyond their immediate environment. This ecological awareness transforms their relationship with the natural world from one of simple exploitation to something approaching partnership. Instead of just taking what they need from their environment, they begin to actively manage ecosystems to enhance their long-term productivity and stability. They develop agricultural systems that work with natural processes rather than against them, creating landscapes that are more productive and more resilient than the original wild ecosystems. They learn to harness natural energy flows like wind, water, and sunlight, reducing their dependence on finite resources while minimizing their environmental impact. But the most remarkable development is their growing understanding of time itself. These conscious beings begin to think not just in terms of their own lifespans, but in terms of generations, centuries, even millennia. They make decisions based on consequences that won't be fully apparent for hundreds of years. This long-term thinking enables them to engage in projects of unprecedented scope and ambition. They begin to actively manage global climate systems, not through crude technological interventions, but through sophisticated understanding of how biological, geological, and atmospheric processes interact across planetary scales. Some groups develop the ability to predict and prepare for natural catastrophes that might otherwise devastate their civilizations. They create early warning systems for volcanic eruptions, earthquakes, and climate shifts. They even begin to develop technologies that might allow them to deflect asteroid impacts or mitigate other cosmic threats. As their scientific understanding deepens, these intelligent beings make discoveries that transform their comprehension of their own place in the universe. They figure out that the elements in their bodies were forged in the cores of ancient stars. They realize that they are not separate from the cosmos, but are literally made of the same materials that compose distant galaxies. This cosmic perspective fundamentally alters their understanding of their own significance. They begin to see themselves not as accidental byproducts of natural processes, but as the universe becoming conscious of itself. They are matter that has learned to think, energy that has developed the capacity for self-awareness. And so, here we stand. 4.5 billion years after that first grain of sand began its cosmic journey, witnesses to the most extraordinary story ever told. From a molten hellscape bombarded by asteroids to a world where matter itself has learned to contemplate its own existence, Earth's evolution reveals something profound about the nature of reality itself. We are not separate observers of this cosmic drama. We are the universe awakening to its own magnificent complexity, temporary arrangements of stardust that have achieved the impossible feat of self-awareness. Every breath you take connects you to those first oxygen-producing cyanobacteria. Every thought you think is enabled by billions of years of patient evolutionary innovation. You carry within your very atoms the memory of stellar explosions, planetary collisions, and countless moments of creative breakthrough that shape this remarkable world we call home. The story continues, and remarkably, we've become conscious participants in writing the next chapter. And so, here we stand. 4.5 billion years after that first grain of sand began its cosmic journey, witnesses to the most extraordinary story ever told. From a molten hellscape bombarded by asteroids to a world where matter itself has learned to contemplate its own existence, Earth's evolution reveals something profound about the nature of reality itself. We are not separate observers of this cosmic drama. We are the universe awakening to its own magnificent complexity, temporary arrangements of stardust that have achieved the impossible feat of self-awareness. Every breath you take connects you to those first oxygen-producing cyanobacteria. Every thought you think is enabled by billions of years of patient evolutionary innovation. You carry within your very atoms the memory of stellar explosions, planetary collisions, and countless moments of creative breakthrough that shaped this remarkable world we call home. Think about that grain of sand you held at the beginning of this journey. It has witnessed the birth of oceans, the rise of continents, the emergence of life, and the flowering of consciousness itself. It has been part of ancient mountains and deep ocean trenches, scorching deserts and frozen glaciers. And now it rests in your palm, a silent testament to the most incredible transformation story in the known universe. The next time you look up at the night sky, remember that you are not looking out at the cosmos from some separate vantage point. You are the cosmos looking back at itself, 4.5 billion years of planetary evolution concentrated into the brief, brilliant flame of human consciousness. The story continues, and remarkably, we've become conscious participants in writing the next chapter. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.